Today's lesson, we're going to be looking at image representation with a focus on how an image is actually represented using binary numbers and then the implications of this on file size. So we need to understand what is an image, specifically a bitmap image. Now, bitmap images are made up of something called picture elements, or more commonly referred to as pixels. You might hear this when you're thinking about your phone and which phone to buy, and the camera itself has 100 megapixels, for example. This is the same kind of pixels that we're referring to. Now, a pixel is a small identifiable area of an image. You can almost imagine it to be a tiny, tiny dot in an image that you're looking at. Now, each pixel is a single color, and this color is given a corresponding binary value, which is used to represent the color. Now, a color can be changed, but of course, this requires you to change the value. We need to be understanding of what image resolution is. Now, image resolution is the concentrations of pixels within a specific area. When you take a picture, you have a specific area in which image is put inside. Imagine a square or rectangle, whatever it may be. This is the specific area. Now, the more pixels we can fit in that specific area, the more dots we have to make up our image. Now, the more dots we have, if you refer to them as dots for now, then the sharper our picture will be. Now, if you look at the picture below, we've got the same set area, but each time the set area has a different amount of pixels concentrated within the area. So the one on the far left is 1 by 1, and if we go all the way to the far right, it's 300 by 300. And we can see the journey that the image goes through in terms of improving its ability to represent an image by using more pixels. So 10 by 10 is more pixels, or has more pixels rather than 1 by 1. Now, as you can see, if we have a 1-bit binary value of zeros and ones, we have two colors, black and white. Okay, and we've actually created what looks like a bolt using a 1-bit binary value, and the one being black. We've actually managed to create our boat. So this leads on to tell us, or show us rather, that each value has its own color. So here we've got 2 bits, and with 2 bits we get a possible combination of 0, 1, 1, 0, 0, 0, and 1, 1. So 4 different colors we can use. Now, the more bits we have, the more possibilities we have for different colors that we can represent. So 3 bits will be 2, will give us 8 possible colors we can use, and so on and so forth. Now, this moves us on to the next part, which is bit depth or color. Now, we've noticed that the more bits we have per pixel, the more colors we can represent. Now, there's a general rule of thumb that we can follow, which is if a pixel is attributed to n number of bits, then that's 2 to the power of n in terms of the maximum representations of color. Now, if you look below, we have 8, 16, and 24. So when we have 8 bits, it's 2 to the power of 8, and that's 256 colors. 16 bits being 2 to the power of 16, and that is 65,536 colors. Now, a higher bit depth gives us a greater range of colors. By having a greater range of colors, we will end up having a better quality of image. Imagine using every different shade of red rather than just red on its own. We will start to have a bit more of an accurate image, but in turn, obviously, the quality goes up, but then the file size is more likely to go up. And we'll be looking at that shortly. So we need to understand how to calculate file size. It's very important for us to be aware of this, not because it comes up in your exam, but also for you to understand the implications of things like image resolution and bit depth. So image file size is determined by the number of pixels used and the number of color combinations available. We've got an example here where we've taken an image on a 2 megapixel camera, which means that we have 2 million pixels. And the color depth of each pixel is 24 bits. Now, for us to find the file size, we'll need to do 2 million times by 24, and that will give us 48 million. The 24 being the bit color depth, and the 2 million being the pixels in the image resolution of a 2 megapixel camera. Now, for us to find out what that is in bytes, we need to divide by 8 because there's 8 bits in a byte. So 48 million divided by 8 gives us 6 million bytes, which is also equivalent to 6 megabytes. Now, it's very important for us to be conscious of the fact that the greater the quality of file or image rather, then the more memory the image will be taking. And in some instances, we have limited storage, so we need to be aware of this and the trade-off that comes with it. Now, sometimes you'll notice if you go to the properties of an image on your desktop, that the file size doesn't actually match up with the actual calculations if you've done it yourself for the image. So in this instance, you got 1000 by 750 and then the 24-bit depth. Now, this is because of something called metadata. Now, metadata is data about data, and this just includes information about the image file, such as color depth in bits per pixel, resolution, date created, and author. Now, all of these little bits of information do increase the file size by a trace amount, which leads to the discrepancies. Now, that's everything for today's lesson. Thank you for taking your time to listen. We managed to look at what a image is, what bit depth is, what image resolution is, how they affect the file size, and what is image metadata. Thank you for taking your time. Please like, comment, share, and subscribe, and we'll see you at the next one. Thank you very much.